Okay, so in this video, I'm going to discuss this question from the model question paper. So this is based on the concept of group homomorphism. So to quickly review what group homomorphism is, like we say two groups are homomorphic if so let's say you have a group G and a group H, right? So let's take this example of like GB set of real numbers and the operation be addition, and HB another group where you have the set of positive real numbers and the operation is multiplication, right? So a function uh, so for a group of homomorphism to exist, we define a function. So in the question, that function is denoted by that alphabet phi. But usually we define a function from G to H like this. F is a function from G to H, right? So like what this function does is if I give an element X of G into the function, right, the output will be an element in H, right? So for example, if f of x is x squared, then if I take an element like 2 in G, then that element will be mapped to 4 in H, right? So that's what it means. So here for this particular example, right, where you have set of real numbers and plus, so the group operation can be different for uh, the groups. They can be same as well, but I took this example so that like the operations are different, right? And the sets are not also not exactly the same. So this is set of real numbers and this is set of positive real numbers, right? Now we have to define a function which maps every element in G with every element in H. So such a function, an example for such a function can be f of x is equal to e to the power x, right? So which means if I give x, if I take x from G, then this function will map it to e raised to x in H, right? So if I give, let's say, if the input I take from G is y, right? Then it will map to e to the power y. So x is an element of G, y is an element of G, then e to the power x is an element of H, and e to the power y is an element of H, and this x and e to the power x are mapped, right? Y and e to the power y are mapped. So for us to say that this is a homomorphic function of there is group homomorphism, this condition should be satisfied. So the condition is this. So f of I take two elements x and y from G, and if I do the operation, right, f of x plus y, that should be the same as f of x times f of y. So here, what I'm doing is I'm taking two elements of G and adding them, right? Then I'll get some number or value. Now, when that is input to the function, that should be same as the operation on the individual outputs, right? So to make it clearer, let's say x is 2 and y is 3, right? Then if I input x to the function, the output will be e squared, right? Similarly, if I input y to the function, the output will be eq, right? Now, if I for before if I add the two inputs before giving it to the function, right, then it will be x plus y, which is 5. And if I now input x plus 5 to the function, the output will be 8 to the power 5. So what this says is, like this function is homomorphic because you can see that here, because if I do f of x plus y, that's same as, right, f of x is e to the power x, right, and that is same as f of y is same as e to the power y. Now using the properties of exponents, that's same as e to the power x plus y, which is the same thing you would have got if you had input x plus y into the function, right? If you input x plus y, it'll raise it to the power x plus y. So if this is satisfied, that's when you say a function is homomorphic. And also, a homomorphic function has this property that if you input the identity element of G into F, the output will be the identity element of the other group, right? So that's a property of homomorphic groups. Now we'll use these ideas to prove this question, right? So here it says there are two groups, G and G prime, and G is mapped to G prime, and the function defined is phi. So they've not given what phi is, right? But what we are asked to prove is this is what we are asked to prove, right? So, like, this is the approach that we use for any proof problem is, if you're given something, you should be able to write a conclusion based on what is given. Some conclusion based on. So here the given fact is G and G prime are homomorphic groups, right? So which means I can use this property here, right? So which means if G1 is an and G2 are two elements of G, then phi of G1 G2 should be same as phi of G1 and phi of G2, right? So here again, we don't know what operation is defined on G and what operation is defined on G prime. That's why we didn't put any operation in between between G1 and G2, or like in between here we didn't put anything, right? That's because we don't know what the operation is, but it should be true for any operation. That's the property of homomorphic groups. So we can write it like this. Now, what you have to remember here is, right, this G1 and G2, they are elements of G. So G1 comma G2, they are elements of G because we have taken them from G. But this phi of G1, right, that's an element of H, because if you input G1 into phi, the output you get is an element of H, right? Similarly, phi of G2 is an element of H, right? Okay. So now, what we need to prove is not about G1 and G2. We need to prove something about G and G and G inverse. So we'll take G and G inverse and apply the same property. So, like, we know that if G is an element of G, then G inverse will also be an element of G because that's a property of a group. The element and its inverse should be in the same group, right? So if I apply that function phi to G inverse, so since it's homomorphic, this should be same as phi of G times phi of G inverse, right? Okay, now what is G times G inverse? So any element operated with its inverse should give you the identity element, right? So that's equal to phi of E uh, G, right? Because EG is the identity element of group G, right? Now this one here, that is phi times G times phi times G inverse, right? These two are elements of H. Okay, now we'll use this property here, which says if you input the identity element of the group on the left hand side, the output will be the identity element of the group on the right hand side. So this here, that will become E G prime, right? Because that's the identity element of the other group. So that's equal to 5 times G times 5 times, I keep putting these dots, but that that it's not multiplication, it's some operation. So G inverse. Okay, now what does this mean? This is saying an element of H times another element of H is giving you the identity element, right? Identity element of that group, because E G prime is the element. So oh, okay. So I used H here, but actually I should have used G prime here, right? Okay. So when you multiply two, or when you operate two elements of G prime, you get the identity element of G prime. So which means one should be the inverse of the other, because that's the property of inverse. So now, so which means this here is right. The inverse of this should be this for you to get the identity element. So, and that's what the question is asking us to prove. So what is the inverse of phi g? So phi g is some element. So its inverse will be phi g inverse, and that is this here. So phi of g inverse, and that's the proof for that question.